Okay, lesson 8, using identities to solve equations. I have to use this. I had to write it all out because I don't have the right sheets for this. This is again another hard unit, but there's no new information here. We need to be able to use identities. We need to be able to rearrange equations. We need to be able to use our unit circle and find solutions. And there's one important kind of special rule in this one in the middle in the investigation, and we'll go over that when we get there. Let's start with the beginning one. So these shouldn't be anything new. We should be able to do this, but making sure we can actually be comfortable with our trig identities. In this left one, this is A. We need to turn it all into something that we can solve. So we're trying to find an x value that makes this true. It gives us the period actually from 0 to 2 pi. So we're trying to find an x value that makes this true. Now we can't do it with a cos and a sine, so we need to turn it all into the same type of trig thing. And we can't really do it with a squared unless we're going to factor it. So we need to have it just say sine of x or cos of x and kind of be factored to be able to solve this. So the first thing we're going to target is this guy over here, the cos squared of x. We can get rid of that and turn that into a sine. Let me shut my window. Okay, so which identity do we have for cos squared of x? We are going to use this identity here. I'll write it up here. This is the sine squared plus cos squared equals 1. This is really one of the most important trig identities there is. This is one that you should have close to memorized, and this should be one of your go-to ones. This is really kind of like, I would say the tan identity is the most important one. I'd say this might be the second most important one. This one is used all the time in many different ways. So if we want to get rid of cos squared, it's going to be 1 minus sine squared. So 1 minus sine squared x plus 3 sine x equals 0. Then we just expand it out. 2 minus 2 sine squared x plus 3 sine x equals 0. And now we have a quadratic. So we were doing this last time where we say let u equal sine of x. And then we could rewrite this as negative 2u squared plus 3u plus 2 equals 0. And then we have a quadratic, of course, and we can be able to factor this quadratic. And when we factor this quadratic, I'm going to jump right to the factored thing because I assume we can do this. It's a decomposition, and it should have a final form of 2 sine x plus 1 and sine x minus 2. After you completely factor it and sub the sine x back in for u. Okay, so now we're getting very close to a solution. Now we just have to solve each half individually. So when is sine of x equal to 2? And when is sine of x equal to negative a half? If we can solve each of these parts, then we can find when it equals 0. This one over here, sine of x is never equal to 2. All sine x's are between negative 1 and positive 1, so there are no solutions from that half. But this one over here we can solve. It should be in quadrants 1, 2, 3, and 4. And the solutions should be 7 pi over 6 and 11 pi over 6. Finding those with your unit circle or your special triangles or any other way you want, but you should be able to start doing this hopefully quicker and quicker It is a good lesson. We should actually be practicing our unit circle frequently. I'll give you a couple extra ones. Maybe we'll do it like every other day. Try and write a really quick one at the end of our class or something. Because you don't want this going from this step to take 5 minutes or 10 minutes. You want this to be a 1 minute thing. Otherwise, you're really going to be hurting for time. Although the diploma, you do get those double time if you want it. So time isn't as big a factor as it could be. Okay, this guy over here. So again, we're trying to solve for x in this one. So we're trying to make it say cos of x equals a number, and then we can find when x is a certain thing based on that. So the pi over 6, cos of pi over 6 is just going to be a number. So that part we want to kind of get rid of and isolate it down to just cos of x's. So we're going to expand this out. So we're going to call this cos of x times cos of pi over 6 minus cos of x times negative. Oh, sorry, I expanded it wrong. Oops, I did that wrong. You can't expand like rainbow. This is actually going to be our sum and difference of cos identities. So this is actually going to take a long one. I'll do the first part in one line, and I'll do the second part in a second line. So the first part is going to be the addition one, so cos of x times cos of pi over 6 minus sine of x sine of pi over 6. Okay, that's the expansion of that one based on the sum identity. And then we're going to subtract the entire second part, which is almost the same rule, but with, what is it again? So cos A, cos B plus sine A, sine B this time. So cos x, cos of pi over 6 plus sine of x, sine of pi over 6. Sorry, a little bit hard to see. Maybe I can zoom in a bit. Okay, so that's using our first identity. Now we turn all of our pi over 6's into just numbers. Really should do this with more room. Maybe I'll write this out on another paper. Just so we can have enough room here. Okay, cos of pi over 6 is root 3 over 2. So it starts out equals cos of x times root 3 over 2. And then we're going to subtract sine of x. And this is going to be 1/2. And then from there, we're going to subtract the entire next part, which is cos of x times root 3 over 2 plus sine of x times 1/2 once again. Okay, now we rainbow this subtracting in, so the first term is subtract and the second term is subtract. And hopefully you can notice this guy and this guy are actually going to cancel. It's going to be a positive one and a negative one, so they're going to cancel, and we're going to end up with negative 2 sine of x times 1/2. All this is equal to 1 still. And then obviously the 2 and the 1/2 are going to cancel out. So negative sine of x is equal to 1. So when is sine of x equal to negative 1? Okay, when is sine of x equal to negative 1? You could look on your unit circle, or you can think in terms of the graph. Sine goes like this. So it equals negative 1 3/4 of the way through, which is 3/4 of 2 pi, which is 3 pi over 2. There's actually just a single solution to this one in the first 2 pi domain. Or use your unit circle, and that's that. Challenging questions. I don't think these are easy. But all the parts of them aren't too bad. I think the hardest part is right at the beginning, kind of figuring out where to go. This one was probably the easier example because you knew you have pi over 6, so you can probably expand it, and then those will just turn into numbers. That should be kind of obvious. This one over here is a little bit harder. You need to start making them all look like the same trig thing. And almost never is it going to be tan. So you're going to try and turn everything into sine or everything into cos. And then often we like to factor that. So this one actually looked like it was going to be a trig one. A quadratic one. And this is a quadratic trig. It did turn into that indeed. So some strategies. Mostly takes practice. You want to get good with it. Okay, try this one down here. Which of the 3 identities for cos of 2x would be most useful to use in this case? So we go down, we have 1, 2, 3 different identities for cos of 2x. One turns it into cos squared and sine squared. We probably don't want that because we don't want to get rid of our cos and we don't have any sine squares anywhere. The other one turns into cos squared minus 1. Again, that's not going to be very helpful because then we'll have coses and sines. So we want the third one. We want to use this identity. We want to use that guy. So let's fill that in. Okay, and then where do we go from there? At this point, you'd want to see if you can get things to cancel out or if you can get things to divide out so we can like get rid of a term entirely. If we could get rid of our sine squareds by collecting like terms or by canceling them out, that would be great. That would make this easier. But we're not going to be able to do that in this case, so this again is going to be a quadratic one. So our method is going to be put everything on one side and factor it. So we'll put it all onto this side over here. So we're going to have 2 sine squared x minus 7 sine x, and then plus 4 minus 1 is plus 3. Okay, we're going to solve that for when it adds to negative 7 and when it multiplies to 6. Well, that's going to be negative 1 and negative 6. But it's decomposition. So 2u squared minus u plus 6u plus 3. Factor by grouping. So we have u, 2u minus 1 plus 3, 2u. Wait, did I do something wrong? Oh yeah, this should be a minus 6. Sorry. That's a minus. This is a plus. So I'm actually going to pull out minus 3, and that changes it to 2u minus 1. Good thing about decomposition is you can always find your mistakes, because these things have to look the same. If they didn't, then you made a mistake somewhere. Okay, so our final thing is u minus 3, 2u minus 1. So we want to find out when sine of x is equal to 3, or when sine of x is equal to, I'm just subbing it in here and moving this stuff to the other side, so 1/2. And this is actually very similar to the previous one, so we should be able to solve this pretty quick. This one does not exist. And this guy over here gives us solutions. Well, it's quadrant 1 or 2. And our solutions should be pi over 6 or 5 pi over 6. Just like that. Okay, so those first two examples are really kind of a summary of what we've been doing in the second 2/3 of this unit. You will see multiple choice questions like this on the test, on the diploma, and they're going to be hard. They're going to take a while. I don't know what to tell you. Good luck. This is definitely, I'm not going to lie, this is the hard part, I think. Some of the other units will look easy in comparison to this stuff. It can take a while, and there's many ways you can go wrong. If you don't know where to go at the beginning, if you don't know how to manipulate these things, you could start manipulating it and you can go completely wrong. So if you're not sure where to start, you might want to start these questions on rough paper, because you can go down completely wrong routes and then just not be able to solve it. So if you find it just getting more and more complicated, then you might scratch out everything you've done, go back to the beginning, and take a little while at the beginning and look at it and look at all your identities and kind of come up with a roadmap of what you might want to do. Don't just start punching in things. These things take a bit of intuition. Okay. Investigation. There's just one special rule we want to make really clear in this investigation, and we're going to use these two examples to highlight it. So they give you partial solutions. They have two students that they had this question, they had this question, and they did the following. So in number one, they divided both sides by cos of x. Cool. That turns the right side into 1, and that turns the left side into tan of x. And then we can solve that. When is tan of x equal to 1? You could look on your unit circle. Tans are a bit hard to find in your unit circle. I would tan inverse on my calculator, and I would find that it equals to 45 degrees, or pi over 4. And then I would know this is also, it's quadrant 1, and it should be quadrant CAST 3. So pi over 4 plus pi is going to be 5 pi over 4. So that's the solutions to that one. According to this person, we're just finishing their solutions. There's going to be an error in here somewhere. This one over here. So they have sine of 2x and cos of x. They use the identity that sine of 2x equals 2 sine x cos x, which is true. And then they divided both sides by cos of x, just like we did here pretty much. So this side became 1 again, and this side became just 2 sine x. So then they moved that to the other side, so they said sine of x equals a half. Well, actually, this part we don't have on there yet, but you would do that next. You'd move that over, find sine of x equals a half, and find your solutions to this. It's quadrants 1 or 2. And your solutions should be pi over 6 and 5 pi over 6. Good. This seems like a reasonable method, and it is only kind of, it's a real picky special error, but it's an error nonetheless. In part 2, we actually did something wrong. So the next thing they want you to do is try and graph these. So graph this expression right here on 2 different lines and see where the points of intersection are. And actually they give you the graphs, so I don't think you even have to do that. So in the first one, there is a point of intersection here and a point of intersection here. They tell you that every line is pi over 6. This last one is the scale. So this is pi over 6. What were our solutions supposed to be? Pi over 4. And this is pi over 3. So yeah, halfway between is pi over 4. That makes sense. 1 pi 6, 2 pi 6, 3 pi 6, 4, 5. That's pi. And then this is pi over 4 past pi, which is indeed 5 pi over 4. So this one works out just fine. We find the 2 solutions are indeed these 2 solutions. So we did correct work in that one. Now in the next one, again, every line, it's the exact same scale, so every line is pi over 6. So there's our pi over 6 solution, like we had up here. And then we need 5 of them. So 1, 2, 3, 4, 5. So this guy down here also is our real solution. So we found these two solutions. But there's a mistake in this one. We are looking for everywhere where these two curves are the same. So we missed out on this guy, and we missed out on this guy right here. There's actually two solutions we failed to find. Okay. And then it starts talking along. Does number 1 agree with you? Yes. Does number 2 agree with you? No. There are two more solutions. One is pi over 2, and the other one is 3 pi over 2. And I'll tell you why. So there's kind of a rule. I'll do a simple version without trig. If we had the equation, when is x equal to x squared? Okay. I would look at it algebraically and look at it intuitively. Maybe you can find all the solutions intuitively. Algebraically, maybe you want to divide by x. So if I divide both sides by x, then I get 1 equals x. So I have my solution, x equals 1. Okay, where did I do something wrong? Is x equals -1 a solution? Well, -1 becomes +1, and that's -1. So no, -1 isn't a solution. But there's one solution we didn't find. The other solution is x equals 0. So there were actually two solutions to this problem. So the thing that we did is when we're manipulating it, so there's proper mathematical ways of manipulating expressions and there's improper ones. And what that really means is, now that we've seen so much about functions, we're not allowed to manipulate the domain. We go back to what we were learning about restrictions way back when. You have to take the restrictions from the original expression and they're not allowed to change. So sometimes you can make them simpler and you forget about a restriction, and that's a problem, and you have to remember the restrictions from the beginning. This is the opposite problem. If we're dividing by 0, we're actually adding a restriction that wasn't in the original one. So this is true so long as x is not equal to 0. But this isn't an actual restriction. This is just something we forgot to check, basically. When we got to that step, we just left out something. We left out the possibility that x could be 0. It's basically the same thing as when you have x squared equals a number, like n. If you try and square root this, so you square root both sides and you say x equals the root of n, you left out a whole bunch. Because you added the root sign, you left out the possibility that it could be a negative. And that's why we have to do the plus negative thing. So these both are kind of the same type of rule. We forget about the new restriction on the domain that we created. And this is really a picky thing. It's very easy to forget. I'm sure I've forgotten it from time to time, but we're going to try and be careful with that. So going back to this expression, we divided by cos of x in this one, and we divided by cos of x in this one. So we left out the possibility that cos of x could be 0. So basically we just need to check if cos of x could be 0 in the end. So in the first one, could cos of x have been 0? Well, cos of x, if it's 0, sine of x, when is sine of x equal to, wait, what am I saying here? If cos of x was equal to 0, then x would have to be pi over 2. The first instance of it would be, is that right? Yeah, pi over 2. Since sine of pi over 2 is not equal to 0, so it will not be a solution in this one. Oh, and we actually do that. We actually just want to check it left side, right side. If cos of x equals 0, which means if x is equal to pi over 2, and there's a second one, which is, you add pi to that, which is 3 pi over 2. But we only have to check one of these. If it's going to be true for one, it's going to be true for both. So this side becomes 0, and sine of pi over 2 is equal to 1. So no. Cos of x is not a solution to the first one, so we didn't leave anything out. But now we should check the second one. What about sine of 2x and cos of x if cos of x is 0? So this side becomes 0. And sine of pi over 2 times 2. There's a 2 there now in this one. So that becomes sine of pi. And sine of pi is, we can use calculator. I'm in the wrong mode, but it is indeed 0. So in the second one, the thing that we left out is actually a real solution, and we failed to find it. So that's just the one special rule on here. There's a whole section on this, so this might be something they ask a concept question about at some point. What did they do wrong? They might even do it the same way, like this person tried to do this. What did they forget? They might show you this, they might show you the 2 solutions they found, and they say, what did they do wrong? And that'd be a hard question, but now you're going to get it right. You're going to say, oh, they forgot to check. They added a restriction with cos of x, so they forgot to check if cos of x could be 0. Okay, and then on the next page, let's go all the way down to E. We're going to do it the right way now. The better way to solve this so the better way to solve this is actually by factoring. So you don't want to actually divide by cos of x out of both halves. You want to move everything to one side and factor is the safer way to do it. So we're going to use the exact same identity. So this is 2 sine x cos x. Now we subtract cos x. Okay. And now everything's on one side. Now all we have to do is factor the cos of x. There. Now we didn't have to divide by anything, so we didn't have to add any new restrictions to check. So now we can actually just find our solutions. So either cos of x equals 0, or sine of x is equal to 1/2. And now we find all 4 solutions, which are, from this one we found out it was pi over 6 and 5 pi over 6. And from this one it is pi over 2 and also 3 pi over 2. Okay. So that's a way of doing it without losing any possible solutions. So whenever you're in, and this is actually not just true for trig, this is true for all types of solutions. You never, if you ever divide by or square root the variable, if you ever do either of these things that wasn't in the original expression, then you've added a restriction. So for this guy, you gotta watch out that x could have equaled 0. And for this guy, you gotta watch out that x could have equaled a negative number. So in this one, you want to do the plus minus, and in this one, you just want to check the if x could have been 0 at the end. Okay, so this is really kind of the very last thing we want to talk about with restrictions. This really ends like all of high school talk. A lot of our grade 12 curriculum has been about domains and restrictions and understanding all possible solutions. Just being really, really careful with these things. And this is kind of our last rule for that. Okay, we have a few more questions. On the bottom of this page, I actually like this question a bit. I'll show you the answers, that's fine. This is 2 different functions. We have f of x is the bold one, I'm assuming. No, f of x is the bottom, the thin one, and g of x is the bold one. It wants you to write a new equation where all the x-intercepts are the solutions. Every single x-intercept of both of them. Can we write an expression where every single one of these things is the solution? And it's actually not too tricky. It's a little bit hard to see at first, but if you do this, if you multiply these two things together, it's just like factored form. So whenever f of x was 0, it'll make the whole thing 0, and whenever g of x was 0, it'll also make the whole thing equal to 0. So you just multiply them, and then every x-intercept from both graphs becomes a solution. What about if there was a solution provided by the x-coordinates of the intersects? What if we wanted these things to be the solutions? Just this point right here, and this point right here. Well, actually, that's kind of what we've been doing all unit long. We just set them equal to each other. When is f of x equal to g of x? That's going to make points of intersection the solution. And then if you want it to be a single expression, you would just subtract the g of x to one side, and then it's kind of all on one side, so it's one expression equal to a number. Okay, that's it for that one, and then we're going to have to solve this algebraically, I think. C, use a graphing calculator to find those solutions. Oh, now they give us the expressions, and use a graphing calculator to find those solutions. Hopefully we can do that. Just enter in both of them into the calculator and find the points of intersection. Or you subtract them. You do f of x subtract g of x, which ends up being plus cos 2x, and you just find the points of the x-intercepts. And they should be at pi over 2 and 3 pi over 2. Pause the video, take a little bit of time for that. I know it's a long video, but we're almost done now. And then there's one more. I think we're going to skip this one. If you set them multiplying into each other, so can you find every possible x-intercept? And you can list all those, and there's many of them. With your graphing calculator, you might get them as decimals, but hopefully you can divide that by pi and get them into the fraction form. Okay. Verify the roots algebraically. This is the important part now. Well, this is a hard part, but we can do this. We want to find all the solutions to this algebraically now. So what do we want to target? Let's just have a look at this thing for a while. So we have a sine squared, and we have identities for that. We can manipulate that around. Actually, let's look at all our identities. If we had a 1 minus 2 sine squared, we could turn it into cos 2, which might be something we want to do. We also have sine squared equals 1 minus cos squared. We might want to be able to do that as well. But I don't think this is actually going to be our priority. I think we're going to target this guy. I think it would actually work either way. You could turn everything into cos of 2x's. But generally we don't want to see this 2x. This is a bad part. Because we want to solve for just x. So we would like it to be just x. So I'm going to target the 2x first. I'm going to try and write that in terms of sines. If I can write in terms of sine squareds, then maybe they'll cancel. If I can write in terms of sines, then maybe I'll have a quadratic. So cos of 2, this is going to be that bottom identity that we used before. So we're going to be using this guy. Cos of 2 alpha is equal to 1 minus 2 sine of squared alpha. We're going to be using that guy. So let's just rewrite it. Okay, expand. So we're going to have plus 1 subtracting 2 sine squareds, and we have 3 sine squareds. So actually we end up with just a sine squared. And for our constants, we have 1, and we're subtracting 2, so we have a minus 1. That's nice. It boils down to just that. We can't really solve for sine squared equals 1. Actually, I think we could do that. But that's not the way they factored it. Because if I move that to the other side, it says 1, and then I square root plus or minus 1. Actually, that's going to find our solution just fine. I'll show you two different ways of doing it. That actually would have been my instinct, I think. So we could solve that. And when is sine of x equal to positive 1? Well, that's at pi over 2. And when is it negative 1? Well, that's 3 pi over 2. And that's good. That's a solution. The other thing you could have done is factor this. This is a difference of squareds. So you could say sine of x plus 1, sine of x minus 1. And from there, you find sine of x equals to negative 1 or sine of x equals to positive 1, and you get the same solutions. So two possible ways. This way might be a little bit safer, but this way is more instinctual as long as you remember the plus minus for the same reason as our last big rule. If you add the square root, you're going to forget about a solution otherwise. Okay, last one. Cos of 2x, 3 sine squared x minus 2. Okay, so we have kind of the same things going on in this one, obviously because it's from the same two graphs. We have the 2x over here, we have the sine squared x over here. But this one actually, there's a trick to this one. I probably would have missed this, but I would have started maybe attacking this cos of 2x. But we don't need to do that because this one is a special case. It's already factored. We already have two factors equal to 0. So we actually have two different solutions in this one already set up for us. One is negative cos of 2x equal to 0. And one is 3 sine squared x minus 2 equal to 0. Which makes sense. If you remember the previous page, this expression down here that we're trying to solve for now was all of the roots from each expression. And all we did now is break it down, say it's the solutions to the first expression or the solutions to the second expression. Okay, so let's find each of those. Negative cos of 2x. Well, the negative, because it has to equal 0, it doesn't matter whether it's positive or negative. So cos of 2x. Now what do we do? Well, we can solve for 2x in this one. So 2x has to be, when is cos equal to 0? Well, that's going to be at pi over 2 and 3 pi over 2. Okay. And then x must be dividing those by 2 then. So pi over 4 and 3 pi over 4. And there's one thing we're still forgetting. You could do it in a couple different orders. I like to do this at the end. Because we were solving for 2x and not just x this time, we have to find all the solutions within our new period. So this was actually, well, we want to go all the way up to 2 pi. We've only found 2 solutions so far, and the period of the original function was every pi. So these solutions should repeat themselves every pi terms. Or both of these are in the first half. We found this solution and this solution. We haven't gone the whole way around the circle yet. Because of the 2x, all of our solutions fell into only the first half, and we're missing this guy and this guy. So add pi to them. We're also missing 5 pi over 4 and 7 pi over 4. The other way you can do that, the way they did it in the lesson, the very first time we saw it, was they said the period for this one we want to expand. We want to do it up to 4 pi and then shrink it down. So they found 2 more solutions here, and then they shrunk them. Either way, don't forget, just keep an eye out every time if you're solving for something not just x, then check your domain. Make sure you found all your solutions after. If it was a number higher than 1, then there'll probably be new solutions. If it's a number less than 1, if this was a half, then some solutions might not even count. This guy might get too big, and he might have to be ruled out. That is what would happen if it was a half x. But yeah, this one over here, well, sine squared x is equal to 2/3. So sine of x is equal to root of 2/3 plus and minus. Is there any way to see that as... We couldn't really factor this one. Not that I know of. Maybe we could have, but not that I know of. This doesn't look like a special triangle to me either. It does have the root 2 and the root 3, but they're never in the same triangle together. So we could do some really hard stuff and try and break it down, but in the question it said you can use decimals if you round to the nearest tenth. So I'm just going to do this one in decimals. So just find what the sine inverse is of root 2 over 3, and then move that into all 4 quadrants. Or plug it in, yeah, I think that's the best way. Use the positive root 2 over 3, and then move it into all 4 quadrants. So the first solution you should find is 1.0. And then we need to do, the second solution is going to be pi minus 1.0, which is going to be 2.2. Then pi plus 1.0, which is 4.1. And then 2 pi minus 1.0, which is 5.3, roughly. Haven't done a lot of rounding lately, but yeah, roughly. Okay, that's it for this lesson. Super long one. It was mostly just extra practice on how to solve these things and that one new special rule. Good luck.